Hello everyone, my name is Tim.
And I'm Chance.
And we're going to talk about?
The pressure temperature chart.
Now, when we're talking about pressure temperature, we're talking about refrigerants. Now, are there different kinds of refrigerants?
All kinds.
So we got
friendly one here?
Well, so will the pressure temperature chart work in this?
Of course. If it's at saturation.
Ah, so this could be just like if it was a rooftop unit, right? Or anything else, a chiller or whatever. As long as the pressures and temperatures have equalized, and there's both liquid and gas there, if I measure the pressure, I can be able to know what the temperature is. If I know what the temperature is, I can plot the pressure.
Correct.
And I can actually plot, if I know both of them, what refrigerant is. So is it just this one?
No, so it's for multiple refrigerants.
So you're telling me, whoa. So there must be a difference in refrigerants on their color.
Yes.
Yeah. And so for example, if I'm using recovery tanks, okay, does the same principles apply that we're going to talk about to this tank as a recovery tank?
Of course. It's all pressure temperature.
And why are there so many different refrigerants?
For different operations.
And different applications, right? And some rules and laws say I just can't use them. Right?
Exactly.
So whichever one I have, you got to find the pressure temperature chart for that. Okay? Now, when I look at the pressure temperature chart, I have a condenser and evaporator coil. Now, what can you tell me about evaporator and condenser coils?
There's always saturation in both of those.
Yep. While it's running, actually they come in various shapes and sizes.
Oh,
so we have one here, okay? So they come in various shapes and sizes. So they can be like this, right? What does it really matter? They could be copper, aluminum, one's more maybe bigger, smaller, depends on the efficiency, but the principle remains exactly the same.
Exactly.
Right? Now, we have this thing called a metering device, right? Now, we know that the type of condenser coil we have, the PTchart isn't here, it's just giving me results. Now tell me about the metering device. Can I have all kinds?
There's all different kinds of metering devices. Copper wires on them.
Wow, we got a thermostatic expansion valve.
Yeah.
What else we got there?
This one.
Oh, ooh, we got a manual expansion valve. What about that big one with the octopus? Well,
high-tech stuff.
yeah, this is pretty cool, right? So it could look like this, okay? It could be something like this. Could we just have a piece of copper?
Yeah, we know simple copper too.
Wow, as long as it drops the pressure. Does the PTchart care?
No.
It doesn't care, right? Doesn't care. It only cares about saturation. So if I have all ice, is this saturated?
No.
No, because it's all ice, right?
Exactly.
However, if I have ice and water, I let it cool down. If I cool it down anymore, it all becomes a solid, ice. If I warm it up anymore,
It becomes a liquid.
all becomes a liquid, right? In this case, I'm dealing with not liquids and solids, but gas and liquid, right? So, in here, can I measure the pressure and convert it to temperature?
Nope.
How about here?
Nope.
How about here?
Nope.
How about here?
Nope.
Only where it's both saturated. No subcooling, no superheating, right?
Only saturation is where you can measure.
Okay, wow. Now, tell me about the condenser.
It rejects heat. As the operation's going, it's always rejecting heat.
And the evaporator?
It absorbs it always.
So,
depending on the ambient.
I know that this pressure has to be lower than the ambient.
Of course.
Okay, so the refrigerant in here has to be colder than the ambient temperature. That's why I use that metering device, right?
Exactly.
Okay.
Just to make sure it's working.
And over here, I need to make sure that the pressure is high enough to make the temperature higher than ambient.
Exactly.
Okay, so if I measure the pressure here, can I convert this to temperature here?
No.
How about if I measure the pressure here, can I convert it to temperature? Man. You
All
really
these limits.
Yes, wow. Okay, so does it matter what kind of compressor I actually have?
No. It just matters on the operation you're doing and the cost efficiency. The cost of operation.
So why would I choose one of these over something like that?
Just depends on what you're doing, because all compressors do is it moves the refrigerant and higher the pressure. So depending on your operation, if you're dealing with a small refrigerator, maybe you'd have a reciprocating. If you're dealing with a different type of refrigerator, maybe a big one, for a big operation, you use maybe a scroll.
But does the PTchart really care?
No.
No. The PTchart reading is the same no matter what I use here. It's telling me basically what's going on in the evaporator, what's going on in the condenser for the refrigerant temperatures and pressures, right?
Exactly.
So it allows me to plot what my refrigerant's doing and to find out if I have liquid and gas in there and all the good stuff, right?
Which is extremely important.
Kind of if I want to cool stuff down. Kind of important to get my beer cold, okay? Okay, now, will that saturation take place here on that chart?
Nope.
Here?
Nope.
Here?
Yes.
So if I look at here, at saturation, it's gonna be some sort of pressure, right? We're just expanding this, is just an illustration. However, once it's at saturation, I add any more energy to it, what is it?
Superheated.
And if I take away any more energy,
It's subcooled.
and the pressure temperature chart won't work here, will it?
No.
It won't work here either. But still is pretty important,
Of course.
because it helps me plot this, because if I know,
Saturation.
if I'm 1 degree above, then it's 1 degree of superheat. If I'm 1 degree below, I'm subcooled.
Subcooled.
So if I'm 10 degrees below, I'm
Subcooled.
10 degrees sub. Wow. Now, let's take a, whoa. This looks complicated. Wait a minute though, there's an app for that, right?
Of course. The Danfoss refrigerator.
Now, when I look at this, don't we also have something like this? Thermostats also have refrigerants or some component, and as the temperature goes up, its pressure goes up, and that's where that thermostat control comes from, right?
Correct.
Also, something like this. This has a fluid in it that's directly related to temperatures. I warm it up, there's some temperature correlation that I can read, right?
Correct.
So it's not just refrigerators,
Oh no.
okay? It's not just air conditioning, right? But there's all different kinds of refrigerant, and we're talking about single blended or equivalent refrigerants right now, right? So all based on the pH chart, the pressure and enthalpy chart. That's where I get all these pressures and temperatures. And there's a, what's the relationship between pressure and temperature?
It's all, that's the main relationship. It's always that everything's based on pressure and temperature.
So as the temperature goes up,
So as the pressure,
At-
temperature goes up, pressure goes up.
and as the pressure goes down,
Temperature goes down.
wow. So direct relationship makes it pretty easy, so we should be able to plot all this stuff, right?
Always.
So if I look at here, and let's say that I have a package rooftop unit, it's 70 degrees outside, I have a standard efficiency condenser, which means that it's designed for 30 degree refrigerant, it's gotta be 30 degrees above ambient, and my temperature is 60 degrees outside. If I add 30 degrees to that,
90 degrees.
so at 90 degrees before 10A, I've got,
275.4.
so what if I have, 70 degree ambient temperature, I'm using 134A, and I have a high efficiency condenser, which I'm adding 20 degrees, so 60 plus, or 70 plus 20,
90.
so at 90, I'm at,
No, 4.3.
makes it easy. And I can do that for all these refrigerants, right?
All of them.
So we looked at the condenser, what about the evaporator?
That's a little bit different.
Oh, it is. The temperatures, this relationship is still the same though, right?
Of course, yes.
So we're going lower temperatures.
Exactly.
So let's say I want, and normally I want the refrigerant colder than the space temperature, right?
Correct.
So if I wanted 10 degrees space temperature, and let's say my evaporator is designed to be a 20 degree delta T difference between the refrigerant and the ambient, I would subtract 20, which would make this.
Negative 30.
So if I had 134A, the pressure would be
28 inches in that.
vacuum. Yeah, because these little marks indicate it's a vacuum, right?
Correct.
So this thing's actually running in a vacuum now. What if I had a requirement for 2 degree product, and I had a 30 degree delta T on the evaporator, and I was using 507? I'd be at 11.0 PSIG.
Exactly.
So there is a direct relationship here, okay? Uh-oh. Does this work in every instance?
No, this is mixed refrigerant.
Okay, now we have mixed refrigerants, we have this thing called Glide and Dew
Dew
Point,
point, bubble point.
and we're gonna have to talk about that, right?
Yeah.
You're coming back to that, right?
Exactly.
I need your help on that,
Of course.
because now I have different pressure temperature guns.
Looks like we gotta figure it out.
Yeah, so come back to us next time, and we're gonna talk about how this all works. We talked about the compressor, our expansion devices, our capillary tube, and we talked about all that fun stuff. So come back and join us again. We'll talk about dew point and bubble point. This is Tim,
This is Chance.
and we're out. Good job. So let's see what it looks like.
Sounds good.